Hi, this is Ali Saidi Ashtiani, and me and my groupmate Shamdar Sanju, we worked on the classification of iceberg. So this is basically a binary classification which giving you a probability of whether the object detected is an iceberg or not. And by setting a threshold, we can decide whether um, it's an iceberg or not. So we use the data set available on the competition website. Each instance is giving us two images from two different angles. We use those two images to create a third image, and therefore we use that third image as our 3D model to actually plot the iceberg. And here is a plot of our iceberg. Um, So we used a convolutional network for this problem, and the reason is obvious that we are dealing with images, and CNNs are known to perform very well on images. CNNs usually have the accuracy of 96%, and therefore we set our goal to 94%. And we'll see how well our model performed. Our metrics are precision, recall, accuracy, and F-score. So basically, we know that precision is how many selected items are relevant, which is the true positives divided by true positives plus false positives, and recall, which is basically true positives divided by true positives plus false negatives, and that tells you how many relevant items are selected. So each one of them is giving us information about how the program is performing and how the data was selected. Therefore, a combination of these two gives us a harmonic output, and which tells us how well our program is performing, which is the F-score. And then comes the accuracy. So we defined all the metrics under Keras. And the reason we are using Keras is because it's running on top of TensorFlow and it's compatible with CNN. And we read that it's actually faster than other methods on CPU and GPU. We also defined the parameter for early stopping. Therefore, our program is not necessarily reaching to the maximum number of epochs that's defined, but depending on that hyperparameter and deciding whether the error is improving or not, it stops the convergence. So here is our model. As I said, we are using a CNN. It's a convolutional 4-layer network and 2 layers at the end. And at the end of this model, we define the early stopping. So let's run this model first and see the accuracy. After running this model, we see that after 12 epochs, we got the accuracy of 93%, the precision of 93, recall of 91, loss of 0.17, and 0.93 is pretty close to our goal, which was 94%. Still, it can get better, and the way of making this program better is by changing the number of layers or playing with the kernel size or pool size or activation functions, so we can try different things and make our program perform even better than this. So while doing this training, we saved our weights into this file. Therefore, we can use those weights to perform on our validation set data. So we use the same weights for our validation set, and we got the test loss of 0.2 and accuracy of 89%, which we can obviously improve by following the procedure that I mentioned earlier. However, we cannot use those weights for our test set, obviously, because we are supposed to predict that. So after running the model on our test data, we display the first 10 instances that showing the probability of the object being an iceberg or not. And here is our output. So as a conclusion, I can say we use the CNN network because we are dealing with images, and the normal or average performance on CNN is known to be 96%. We reached to 94% on our training set, 89% on our validation set, but we can improve it with changing the number of layers or playing with the parameters or hyperparameters in our model to perform better. We use the metrics accuracy, recall, precision, and F score to examine our model, whether it's performing well or not. And we use the earliest stopping so that we avoid overfitting and also stop the convergence when the error is not improving anymore. And we use the same weights on our validation set, and we got the error of 0.2 and as I said, the accuracy of 89%. We were also able to use the dataset to plot the iceberg. So in our future job, we are going to display the confusion matrix. We are going to play with the number of layers and the parameters to change or improve the performance of our system. Thank you.